So we're going to talk about some of the applications of integrals, especially of these definite integrals, and what they mean, what they're representing. Because we talked about how it's area under a curve kind of accumulating, but what does that mean? Specifically, what am I doing if I'm taking the integral of a derivative? Right, so remember, a derivative is a rate of change, right? And if I'm taking the integral of that rate of change, I'm talking about how much of that quantity, right, has accumulated. What is the net change in that quantity of function f? Right, so I know that an integral is an antiderivative, right? I know that that definite integral is taking that antiderivative and evaluating it at the end, right? Subtract evaluating it at the start. And so if f prime is a rate of change, f is the quantity of that function, and I'm finding the difference. I'm finding the total amount between start and end. So something like this, a chemical flows into a storage tank at a rate. So they're telling me a derivative of 180 plus 3t liters per minute, where t is the time in minutes between 0 and 60 minutes. Find the amount of chemical, right? So now I'm asking for an amount. I'm asking for a total amount of chemical, no longer a rate, into the tank during the first 20 minutes. So I know, let's call it F for flow rate, or let's call it C for chemical. So if C is the amount of chemical, so C of T is the amount of chemical at time equals T, right? C is dependent on T. C prime of T is the rate of flow of chemical with respect to time. And so C prime of T is what they've told me. C prime of T is 180 plus 3T. And so if I want to go back to an amount, I'm integrating. I'm taking an antiderivative. And so the integral of 180, so C of T, is the integral of 180 plus 3T dt. Now, if I talk about that as a definite integral, right, because CT is going to be a function. It's going to tell me the amount of chemical. I'd like to know the amount of chemical in the first 20 minutes. So what that is how much chemical did I have at 20 minutes, subtract how much chemical did I start with, and that tells me how much is that has flown into the tank. And so what I'm actually looking for is I'm going to take the definite integral between 0 minutes and 20 minutes of 180 plus 3t dt. So I'm going to anti-differentiate. I'm going to get 180t plus 3 over 2t squared. I'm taking a definite integral, so I'm going to skip that plus c. I'm going to evaluate from 0 to 20. And so I'm going to do upper bound, final value. This is a function, so this specifically is my amount of chemical function, right? Missing that constant term, but I'm accumulating, so it's going to cancel out regardless. And so I sub in, I say, how much chemical did I have at 20 minutes, give or take, without that C value? Minus, how much chemical did I have at the start? And it looks like it was 0. And that's going to tell me 180 times 20. So 3,600 plus another 800, it looks like. I'm getting 4,200. And I'm going to check my units. If C of C prime of T was in liters per minute, so this is in liters per minute, when I anti-differentiate, I'm getting rid of the fact that it was with respect to time. And so it turns it back just into a liter measurement. So within the first 20 minutes, 4,200 liters flowed into the tank. Right now, we don't know anything else. Maybe there was a leak in the tank. Maybe I don't actually have that much in the tank. But that was the rate of flow. That was the accumulation of that rate of flow. And so that's great if I'm starting from time 0. But sometimes I have an initial value. And so same idea. Fundamental theorem tells me that the integral of a derivative is that difference in those functions. And that's what a definite integral is. Now, it tells me two different things. It is final minus initial. And specifically, if I have some initial amount, that is f of a. That is how much my current value is, my current function capacity is at that original, that lower bound of my integral, at the starting point, basically. And so if I rearrange this, if I add f of a to both sides, I get this different, slightly different looking function, but it's the same thing. But it allows me to deal with an initial value, right? And it's saying my initial value, f of a, plus, let me do this a little better. So my initial value, f of a, plus any accrued value. So this is how much I'm gaining. This is how much, or losing, right? Whatever's happening, that change, the integral of that change, tells me my final amount. And so water is leaking from a tank at a rate of the square root of t plus 1 gallons per minute. 10 minutes after the leak is discovered, there's 60 gallons of water in the tank. How much water was in the tank when the leak was initially discovered? And so notice again, I've been given a rate. This is the key word here. Gallon, and then I see those units, I see gallons per minute. And so if I'm talking about amount of water, if W is how much water is in the tank, then W prime is this function. And specifically, it's a leak, but this function is actually increasing. So I should make sure that in this case, because of the context, it's going to be a negative value. Usually I'd give you that in the question. I wouldn't make you extrapolate that kind of data. But so W prime, I should have something that's decreasing. I should be losing amount, right? So I should have a negative function. And so 10 minutes after the leak is discovered, there are 60 gallons of water in the tank. How much water was in the tank when the leak was initially discovered? And so I have my initial amount, and then I gain, or I lose some amount of water, from the tank in those first 10 minutes. Right, and that's the accumulation of water from that flow. And again, we use the word accumulation, but I'm losing the water in this case. And that's going to be equal to how much water there is after 10 minutes, right? How much did I start with plus how much did I lose? Again, it's going to be a negative value. And then that's going to tell me how much I have at the end. And so I actually know my final amount. I'm going to have to solve for W0. 10 minutes after the leak is discovered, there are 60 gallons. That's W10. That's an amount. So it's not a derivative. It's not a rate. It's an amount. And then I can solve that definite integral. So W0 plus from 0 to 10 of negative square root of t plus 1 dt is going to be equal to 60. Now, we haven't gone over how to integrate these functions just yet. So we can plug this into a calculator. All right, so here I've just typed it into Desmos. We'll look at this on a graphing calculator in the future, but it gives me a value. And we'll look at how to solve this algebraically in the future as well. But it gives me a value of negative 23.655. So let's go back to our notes. And so W0 minus 23.655 equals 60. I'm going to add that from both sides, and I get 83.655. And so what that tells me, there was 84 liters in the tank when the leak was discovered. So that's just the first kind of idea about what these integrals are actually kind of telling us about situations, how integrals and derivatives are related, and how I can use both of those things together to solve a lot of problems, talk about how those rates of change are actually having an effect on total amount.